I want to say at the outset of this discussion on physical philosophy that I don't consider myself to be smart. I'm not even sure what smart means. I hear intelligence is your ability to focus, or maybe that's IQ. What I do know is that all the good ideas I ever had came from outside of me. My brain is just a very complex organ that stores perceptions. It doesn't think. Ideas don't come out of your brain. It's like RAM in a computer, very sophisticated RAM, but nonetheless, it is a storage medium. What takes place in your frontal lobe, your consciousness, free will, your thinking is not a function of the brain. The brain is involved to assist you with past perceptions. So like I said, I don't consider myself to be exceptionally smart, but I have observed many things in my many years, and I just want to share my observations. If you don't agree with me, that's fine. You're not my enemy. And you're not going to be my enemy. I refuse to make people my enemy. Darkness and no vision, no information, no knowledge, that's my enemy. So, love yous all, and here we go. This discussion is going to be philosophical. It's not going to be programmable logic controllers or industrial automation, but it's going to be physical philosophy, which we call physics. In particular, I think as you mature in your context or develop your context about everything around you, that you become more intrigued with what you can't see than what you see, or what you see caused by things you can't see. We're going to be talking about force in the fields or force fields. I know that sounds like Star Wars or something, but we are all familiar with forces that have fields. Probably the initial one as you're growing up is magnetic fields. And I don't know if you can all recall when you were a child and you got a hold of your first magnets and started playing with them, and you noticed that as you got the magnet close to something like a paper clip or nails, that the lighter with the less mass jumped over to what had the most mass, the magnet, because magnets are heavy. Or you were holding on to the magnet and had it clamped down on the table, so to speak, with your hand, and then things that were heavier than the magnet kind of shifted over to the magnet. You, at a very early age, we all realized that we're things that do things that we can't see, and we can't define them. Now, growing up, I thought if I went to school long enough and studied long enough that I would come to understand magnetism, light, gravity, and the whole 10 yards. Boy, was I in for a rude awakening at some point. We're talking about force fields, and first of all, are they visible? I don't know of any that are visible. People might say, well, yeah, you can see them. If I release something from my hand, gravity pulls it to the earth. No, that's a behavior. You can see the effect of a force or a field, but you can't see it. It's not visible. Visible implies you can see it with your vision. Is it sensible? I had a hard time coming up with a word that described something that you can perceive with your senses. And that is the origin of this word. It's kind of gotten mutated through time to a conclusion rather than its root word of senses or sensing. So can you sense? That would mean in your five senses, do any of them respond to these forces that aren't visible? Again, I would say no. Somebody might argue that they can wear a piece of clothing with magnets and they can feel the difference, but we don't want to go off into the weeds. Let's try to keep this as clean as possible. Are they perceptible? Yeah. With the magnets, you perceived that there was a field or something that extended either from the paper clips to the magnet or from the magnet to the paper clips. And when you proceed a little bit, eventually you realize that the paper clips were the object of the affection of the magnet, not the other way around. How many types of forces or fields are you familiar with? We know there's obviously magnetic, then there's electromagnetic, there's electrostatic, there's gravity, there's light. Some might want to argue that light doesn't have a field. We know that it's been demonstrated that light has behavior of both particles and waves of a field. We'll just say that light has a field, and I don't know, maybe you can think of some others. Those are the main ones that I can think of. Now, the next question is, what is the extent of the field? And this brings up something called the inverse square law. And this is very easily demonstrated. It's one you typically learn about fairly early because you can demonstrate it with a flashlight and you can see it all around you. And that basically says that the intensity is inversely proportional to the square of the distance between the source of the force and the object of interest. Or we'll just put the I intensity equals, it's a value of the intensity or the constant related to the source power. If it were sunlight or a flashlight bulb with a battery pushing it, we would say K represents the lumens at the surface of the lens on the flashlight. Intensity equals that level of luminosity divided by the square of the distance. The intensity at the location of your interest, where you're at, is equal to the intensity of the source force divided by the square of the distance between the source and the location of your interest. It's inversely proportional to the square of the distance. The intensity at any location within the field is equal to the intensity of the force at the origin divided by the square of the distance between the source and that location. Now I'm repeating this because this is important to what we're going to talk about as far as observation of effect from a field on an object that you can see. You can see the object and you can follow its behavior, but you don't see the field. And here's a good image of something we can all relate to because we know what eggs are. We recognize a tape measure. We see a light source, and then we can see that we are incrementally adding 6 inches space between the objects. So going from 6 inches to 12 inches, the amount of lumens striking, the amount of energy striking the egg at 12 inches is 1/4 of what it is at 6 inches. Remember, it's inverse square. If we increase the distance by 4, going from 6 to 24, we've reduced the amount of lumens striking that egg by the inverse of the square. But you can see with your own eyes that when you get out to 48 inches, obviously the amount of light striking that egg is not equal to what it is at 6 inches. That's going to be a very important point here as we continue on. And this is what it looks like in we'll call it a diagram, and this is representing something called steradians. Not radians, but steradians. And a globe or a sphere is 2 pi steradians, where a circle is 2 pi radians. But we do have a radius here. If you take if you want to call it the origin in the center there, as the light diverges out, because remember, whatever the luminosity is that at the center, it is diverging out over the entire inside of that sphere. So that whatever light is coming from the source lights up the entirety of the inside surface of that sphere. If the light at the source equals the light collectively on the inside of the surface of the sphere, they have to be equal, ignoring any losses due to atmosphere inside the sphere, but they should be equal. But it's more spread out. The intensity at the radius of that sphere on the surface of the sphere is going to obey the inverse square law. This is another diagram that shows the divergence of the energy as it extends out from the source by radius, 2 times radius, 3 times the radius. If you look at that rectangle at point R and you double that distance, that rectangle is now expanded out to be 4 rectangles. And if you go 3R, it's 9 rectangles. 3 is cubed is 9. I think we all agree with this, but I want to cover the bases here just to get everybody thinking in terms of how fields behave. And conversely, if you reverse this, I should say, and let's say that you have a light source at 3R and you're focusing it on R, through R to S, that what the light that hits the lens, the magnifying glass at 3R, and is focused to the origin, is going to be extremely intense. Even at R, it's 9 times as intense at R as it was at 3R, if you're using a magnifying glass. We all did this as kids, lighting a piece of paper on fire with a magnifying glass. Okay, so if you comprehend and agree, that means understand. Comprehension and understanding are not the same thing. Comprehend means that you grasp the point somebody's trying to make. You comprehend the idea, but that doesn't mean you agree with it. Understand implies comprehension and agreement. If you understand this observation of the inverse square law, and you agree that the interaction between the force field is not equal everywhere in the field, and we just demonstrated that because if you're anywhere inside the sphere, the amount of lumens that are going to strike the object is not equal. Now, on the surface of the sphere, anywhere on the surface of the inside of the sphere, the lumens would be equal at that distance. At the same distance from the source, it's always going to be the same value. The inverse square law then becomes a postulate in your thinking. This became a postulate in my thinking many years ago when it was first introduced, and I could demonstrate it to myself, and I found no exceptions. A postulate is a thing suggested or assumed as true as the basis for reasoning, discussion, or belief. Every bit of scientific reasoning or scientific process has to begin with some postulates. If you don't accept the inverse square law as a postulate, then going forward might be just a little sketchy. Okay, if the distance is increased to infinity, in this formula, if distance is infinity and you square it, that can't get any more than infinity, right? If the distance is increased to infinity, does the intensity become 0 or approaching 0? Well, it's never going to become 0, but it can approach 0. That simply means that if you're at 10 and you go to 1, you're approaching 0. But when you look at graphs, when you're doing analytical geometry and other kinds of math that involve curves on an XY axis, a lot of them don't start at 0 and then they never really reach a terminal value. In other words, they approach. It's just like time constants for RC time circuits, where you're charging up a capacitor through a resistor. It charges 66% in one time constant of what's left, which means there's always something left. But it never really reaches maximum, never really starts at 0. Now, is there any transfer of energy without a field? Can you think of any instance where there's a transfer of energy without a field? If you think about a electrical generator and you're using a magnetic field and you're applying a mechanical force to that magnetic field to push the field through the wires, which forces the electrons in the conductors to move. To transfer energy, there has to be a field. And we're talking about looking at what happens in the physical world, in the classical physics realm, when you see something happening, but you don't see what's causing it. Now, you may perceive what's causing it. You may even think you know what's causing it, but you can't see it. And you might be tempted to cite an instance of energy transfer without an obvious field. You might come up and say, well, if I grab a bicycle tire that's stationary, is not spinning, and I grip it with my fingers and I spin it on the axle, that does not include a field. Well, actually it does, but we don't want to get it off into the weeds about the interaction of one solid with another. We'll just say, for the sake of our argument, is there's no transfer of energy without a force field, without a force or without a field. What do we conclude then? If we observe energy transfer that seems to be at the same level regardless of the location. We just went through and demonstrated that as you move out away from the source of the energy, the source of the field, that the effect is inverse square related. Well, what if you observe an energy transfer in a situation where it seems to behave the same no matter where you put it? In other words, there is no variation. The source of because really you're thinking, in some cases, the source of energy is internal to the location. If I take an object and put it anywhere in the universe and it behaves the same way as far as energy goes, then you might want to say that the energy is internal to that device. Or the source of energy is external to the location, meaning the item where it's located, but there's no finite origin in terms of classical physics. These are the things that we're talking about. We're not talking about the fields that we learn about in classical physics that we can model, we can duplicate them, repeat them. In other words, we can mathematically model them. I'm going to present an instance here where there is no finite origin in terms of classical physics. So you have to ponder it, and it really should stretch your mind. All locations are equal distance from the source. What do we include then when we observe energy transfer that seems to be at the same level regardless of the location? One was that it's internal to the object. The other is that it's external. But let's go one beyond that. Let's say that it's not internal to the object, it's external, but no matter what location you pick, anywhere in the universe or anywhere in your world, our world, that the reaction is equal. You would have to say then that all locations in the field are equal distance from the source. Now, there are no fields that we can mathematically model like that. We're kind of bumping into the quantum realm out of the classical realm, which I think interests a lot of people. I won't say that I comprehend it, but I understand it in the sense that I agree that it's there and I believe it, but I can't comprehend it. That may not fit well in your noggin, but there it is. Let's examine one instance where this appears to be true. Now remember, the instance is that an object is going to receive a transfer of energy and it will receive it equally the same no matter where it's at in your world. We're going to pick a mustard seed. Okay? A mustard seed, I just picked a mustard seed because it's extremely small, and if you try to measure if there's anything in that mustard seed, any energy in there, with all known instrumentation, you wouldn't find any. No one has ever found energy. You might find potential energy in that you could take a whole bunch of these, light them on fire, and they would burn up. But there's some potential energy in that sense of oxidation. But I mean, there's no energy in this seed to provoke what's going to happen when you plant it in soil and apply water to it. If the behavior or the energy transfer is the same no matter the distance from the source, because the source has no finite distance from anywhere, it's equal everywhere, you have something called unity. The formula changes from intensity equals the source value divided by the inverse square of the distance. It just now becomes unity, which means that there is no variation in energy transfer no matter where this mustard seed is located in the realm. Imagine that seed growing to that size. Now you might want to argue that that tree did not grow from that seed. Okay, and I'm going to straighten that up here in a minute. It's quite a big tree. You have to ask yourself, how does the energy get into that seed to take the information that's in that seed and consume tons of soil. I'm even going to say tons of sunlight, because photons do have mass. It's been proven that they have mass. What is the force that drives that seed to grab soil and eventually sunlight and grow into this massive plant? Now, if you want to argue that that's really not a mustard tree and it doesn't come from a seed like that, then let's take a smaller one. I still find that fascinating, how something with no energy in it can react to conditions of water and available building materials, the minerals in the ground, and take and convert the soil into an object that big with a root system, because remember, the root system equals the branches. If you could pull this out of the ground and shake the dirt off, the roots would look somewhat like the branches, equal because they support it. However, I know that when people go to Google mustard seeds and trees, they want to argue what plant or tree the person was speaking of when they compared the size of a mustard seed to the adult plant. And they said that it grows large enough where the fowl of the air can roost in it. Now, I know why they attack the mustard seed online. If you go to Google, they're going to attack it. I thought, okay, I'm going to put a move on you. I'm going to pick a seed and the eventual plant that nobody's going to argue with. I come up with this seed. This seed is less than 1/4 inch. That is so small that I could hardly, it almost weighs 0. Now, it does have a physical size, 1/4 inch. It's not round, it's not a spherical shape, but it's 1/4 inch or less. You could say 176 microounces. I said that wrong the first time. My apologies. Nonetheless, where is the force coming from that is applied to that seed on that fingertip to evolve itself by taking 4 million pounds of soil, atmosphere, sunlight, and creating an object of 52,000 cubic feet, 275 feet in height, and even more, a base of 36 feet in diameter? But you need to ask yourself, what is the force? Because no matter where I apply this seed on the face of the earth, in soil where there's water and sunlight, it's going to transform into this, no matter where. Now, I realize that there are places on the earth where the temperature is warmer, cooler, but I'm saying all things being equal, there are billions of incremental locations on the face of the earth where this tree would grow from that seed. And it does it in the exact same way anywhere inside of the field. What I'm presenting to you is the idea that there are fields that you cannot mathematically model in classical physics. And the fact that they're in quantum mechanics, physics, that also says that you can't model it there either, and that's what makes it quantum. Because remember, quanta is energy. That's what we're talking about, is transfer of energy. Now, a couple more things to consider. There's something called 0-point energy. You can Google it. That's the lowest energy state in a quantum mechanics, even at absolute zero, given the equivalence of mass and energy expressed by Einstein's theory of relativity. Any point in space that contains energy can be thought of as having mass to create particles. Energy equals mass, speed of light squared, or let's just say mass. Energy equals mass, mass equals energy. Any place that there's energy, it could create particles. And we know, I had a previous video that I put on this channel that explains how atoms and molecules can be near 100% void of anything. It's just space, nothing but energy. But you can't see through it, you can't put your finger through it, you call it a solid. The reason I bring up 0-point energy is because there's a lot of, we'll call it mathematical speculation. Remember earlier I talked about the curves of behavior on a graph. Most of them don't start at zero and they never reach maximum. They just have a shape, and the bulk of all of the known instances are on the main slope. They kind of fade out at the inflection points on the curve. However, long time ago, one of the assessments of 0-point energy that I read said that mathematically, when they extrapolate observable physics, classical physics, in the 0-point energy thinking, that they said that if you removed all energy from a cubic centimeter, all energy, absolute zero temperature, all energy, that there's still some vibration. There's still something in that space, and it mathematically calculated out to be almost unlimited energy. Now, I can't fathom that, but when you think about what we said earlier about any point in space in the universe where there is energy, there is the probability of there being mass or the capability of there being mass. So we're heading someplace with this. I'm going to continue on with this with other more controversial areas of deciding what these energies or forces are. For a plant, we would probably call it the force of life. So I'll end it there, and we'll pick this back up later. Thank you for watching.